Okay, very good. So I have started the recording. Thanks for joining us. This is the first session of the new series ALET, which is the local version of AMET. And although I don't like the name, it was chosen by my co-organizer, so I was outvoted. Yeah, so it's really good to see all of you. And the first speaker of the series is going to be Jun Zhang, who I guess all of you know, so I want to introduce him. Jun, the floor is yours. You have until 1 p.m.
Okay, thank you very much, JC. Yeah, first of all, I would like to thank Antonio and JC very much, for having me for this first ALES seminar series. As you can see, today I'm going to talk about some kind of not typical theory, okay, but it's kind of in the intersection of theory and the econometrics methodology. Okay, and the title of the paper is called Non-Parametric Identification of Bayesian Games on the Exclusion Restrictions. Okay, so this is joint work with Tong Li from Vanderbilt University and his student who actually graduated this year, and right now she's actually starting work in University of Alabama. Okay, so so let me start with some introduction and motivation for this paper. So as you know, Bayesian games, sometimes we say it's kind of games on the incomplete information. I would say maybe one of the most important models in economics, which actually contributes Hassan's Nobel Prize in 1994. Okay, so while it's kind of natural to add incomplete information into most of the games we have, we know, right? Bayesian games are very hard to analyze theoretically in general. Okay, so the reason is that the equilibrium for Bayesian game is pinned down by integral equations. Okay, which is impossible to solve even for simple distributions such as uniform distribution. Okay, however, for Bayesian game, there's one exception. That the exception is auction, which contributes to several Nobel Prize directly or indirectly. And one of the reasons why auction is easier to analyze theoretically compared to the general Bayesian game is because the equilibrium in auctions are actually pinned down by differential equations. Okay, and we know that solving a differential equation is actually much easier than solving integral equation. So as you can see, there are many theoretical results in the auction theory. Okay, and this also makes the analysis of the auction quite different from the analysis from the for the general Bayesian game. Okay, and because of the success and the insights from the theoretical work, non-parametric identification has been very extensively studied in the structural analysis since the pioneer work of Gorey, Perrin, and Wang in 2000 in the econometric piece. So the question in that paper is very simple. Okay, so we know that in auctions, what is usually observable are the bids from the players. And what is unknown as the econometrician or the researcher is the underlying distribution of variations. This information is very important because many of the, for example, optimal result price is going to depend on the distribution of variations. And also think about, you may have a kind of bidding cap, bidding floor, things like that. The optimal one always depends on the underlying distribution. So the question is whether, from the observed bids of the player, can we recover the underlying distribution of the variation so that we can do some kind of counterfactuals, right? And this is the question in the auction, in the structural auction literature. Okay, and this, as I said, the methodology by Gorey, Perrin, and Wang, their methodology has been extended in many different ways to utilize the data in the real life auctions. Okay, and in fact, this now has grown to be one of the most fruitful fields in empirical I/O, which is called the structural auction. Okay, however, we know that auction is just one specific application of Bayesian game. Okay, because it's kind of games on the incomplete information. Okay, and we are in an auction. And of course, one natural question is whether this kind of a non-parametric methodology developed for the auction can be adopted to analyze general Bayesian games as well. Okay, and surprisingly, there are very few such studies. Okay, so far we are only aware of 2 papers, and these 2 papers only consider other applications of Bayesian game. Okay, so the first one is He and Huang in 20. So this paper is published like this year in IER. So what this paper does is to look at to using this kind of non-parametric method to look at the Taylor context on the incomplete information. Okay, and another paper is Aya and Zensenko in 2019. This is a working paper, and they used the non-parametric method to look at oligopoly models, like on the incomplete information. I see someone has a question. Yes, please.
Yeah, I mean, I wanted to ask at some point, so might as well interrupt you here. Sorry for that. But one thing is in the structural econometrics, the Gare, Perry, and Wong approach. I think it's not just a differential equation that pins down the distribution, right? They have to assume IID so that you know what's the equilibrium of the first price auction, etc. And then you're going to use the structure of the equilibrium to the knowledge of the structure of the equilibrium bidding function to recover from the distribution of bids. There's a one-to-one mapping to the distribution of types.
That's right.
I think that's it's not so much whether or not there's a differential or integral equation that pins things down.
That's right.
But there may be more importantly, in that I don't know whether you're aware of Brad Larson and Anthony Zhang's work on non-parametric estimation using the revelation principle. Right? You have a Bayesian game, it has an equilibrium. If I observe different actions for different players and then different payoffs associated with these different actions, then I can uncover the distribution of types that gives rise to that. So you don't have to know anything about the equilibrium behavior in the model other than assuming that this is equilibrium and you observe actions and then use the payoff equivalence theorem to infer the distribution of types, basically.
Yeah, that's right. Yeah, so yeah, I think like Simon actually made a very good point. So the reason I say this kind of like a difference between this kind of integral equation, integration, like an integral equation and the differential equation is from the theoretical perspective. Okay, so I'm not saying that's going to bring us any problem with the structural estimation. Okay, but like in Bayesian game, so for all of this kind of games, we are going to assume that the equilibrium is determined by the first order condition. But in auctions, the first order condition is a differential equation. Okay, which is like with ID and symmetric, it's kind of easier to solve. But for general Bayesian game, okay, even if it's pinned down by first order condition, however, it will be an integral equation. Okay, but the integral equations usually do not have closed forms like solutions. But I'm just saying this is kind of difficult for theoretical reason. Okay, and that's why there's not too much work on solving the equilibrium for general Bayesian game. Okay, but for auctions, we know there are lots of results we can derive. But for general Bayesian game, it's really hard to get any closed form solution for most of the Bayesian game.
So I agree with that. I'm just saying that the Larson-Zhang approach was dispensed with that because they don't even assume that they know what the equilibrium is. They just know that if there is an equilibrium by the payoff equivalence theorem and direct mechanisms, there has to be a mapping between the outcomes and the type.
That's right.
So maybe the way to reconcile what you are doing and what you are saying with that paper is that if I'm correct guessing, what you're going to do is you're going to say we want to use the knowledge of the equilibrium. Is that what you're going to do? You're going to use the Bayesian equilibrium of the game to do something.
That's right.
Okay.
Yeah. So in terms of the approach, I think like it's similar. meaning that we're going to have some kind of a properties for the equilibrium, and from the equilibrium, we can recover the underlying distribution using the observed actions.
Yeah.
Yeah.
Okay, thanks.
Yeah, thanks very much, Simon. Yeah, so I think I stop here. Yes. Yeah. So a natural question is, can we go beyond auctions, right? Meaning that for a general Bayesian game, can we like utilize this kind of structural method to recover the underlying distribution of like the types in general Bayesian game, okay? By utilizing the observable actions in those kind of games, okay? And like you may ask, okay, why should we care about structural estimation? Well, I mean, like the reason maybe too obvious for empirical economists. The reason I put this here is because this is a theoretical seminar. So the short answer is basically this allows us to carry out counterfactual studies, right? Because when you know the underlying distribution of the model, then basically you can calculate like lots of counterfactuals. Okay, so potentially this is kind of important exercise. Okay, so what do we do in this paper? Well, we are going to allow an arbitrary Bayesian game within the private type paradigm. And we are also going to assume additive payoff structure that admits strictly monotone equilibrium strategy. Okay. And although like this kind of a framework put on some kind of restrictions on the game we are going to consider, however, this framework is generally enough to cover many applications, such as title contest, oligopoly competitions, diamond search, public good provision, and among others. Okay. And to address the identification issue, we focus on the case where a part of the payoff function is unknown to the researcher. Okay, so basically like in the GPV, the 2000 paper. I mean, the starting point is you have a kind of model like in which the only unknown is the underlying distribution of variation. Okay, but of course later on this kind of methodology has been being developed to cover the case. Well, some unknown like payoff structure, for example, risk aversion can also be accommodated. And here we are going to do similar things in the sense that not only we are going to allow the underlying distribution of variation is unknown, we also allow part of the payoff structure is also unknown. Okay, and that's why we need to assume this kind of additive payoff structure, which you you are going to see like in the next couple of slides. Okay, and what we are going to do.
Can I ask a quick question, Jun?
Yes, please.
Do you need to have the equilibrium strategy to be continuous?
That's right, because like we are saying, yeah, that's right. Yeah, the strategy.
You didn't mention it. That's why I'm asking.
Yeah, that's right. Because in the auction, you usually would not say strictly increasing continuous bidding strategy, right?
Okay, I see. I see.
Yep. Yeah, but like a continuity, yes.
Okay.
Yeah. And so in this paper, we're going to provide the non-parametric point or partial identification results on the distribution of private information as well as on the structure of the Bayesian game. And we are going to introduce the like what is commonly known as the exclusion restriction in terms of exogenous participation. We are going to talk about that like in detail like later. Okay, so basically the idea over here is like we know that this kind of structural methodology can be used to analyze auction. Okay, but now we are saying actually the similar method, okay, similar method can actually be adopted to analyze any Bayesian game, okay, which is a much larger set of the games, okay. So here's a little bit literature review. So theoretically, our paper will be is going to study the general Bayesian game, right? So that means we need to find some kind of the existence and uniqueness for the equilibrium. So for this part, our paper will be built on several existing papers on the existence and the uniqueness of the equilibrium for general Bayesian game. And I listed several important papers over here. But this is not our main contribution, right? Because our main contribution is assuming the existence of the equilibrium and perhaps the uniqueness. How can we do the structural like exercise? Okay, and in this paper, turns out it will be more related to the to the non-parametric identification auction model, okay, but with the exclusion restriction, because this is also the restriction we are going to like impose in our paper, okay, because we want to recover on top of the private distribution. We also want to recover what is the owner payoff structure. Okay, so we need to utilize this this kind of exclusion restriction to get that. And for auction with exclusion restrictions, I've listed several papers over here. So this is GPV, but this is another paper dealing with auction, first price auction with risk aversion. And in their paper, the owner structure is the risk aversion part. Okay, and also there are like some other papers. And it turns out even if we impose the exclusion restriction, okay, in contrast to this GPV paper 2019, because in their paper they can always have point-wise like identification. Okay, turns out that in our paper for general Bayesian game, it's not a case that you can always achieve point identification. Okay, because whether you are going to get the point identification is going to depend on when you change the number of players, whether the bidding function is going to cross with each other or not. And we know that for first price auctions, like when you change the number of players, the bidding function always cross at the lowest variation. So basically, there's always a crossing in the GPV paper. That's why they can always get the point identification. However, in our paper for general Bayesian game, when you change the number of bidders or when you change the number of players, the two action function may not always like intersect. Okay, and when they do not intersect, actually we can show that you cannot have point identification. The only thing you can have is a partial identification. And that's why our paper is also related to the paper with partial identification. Okay. Yeah, and this is about the introduction and the literature. Any questions? So as Simon said, like what we are going to do is similar to this kind of using Bayesian, like the relation principle to connect the action and the type, right? But we are like looking at the framework of Bayesian game instead of this kind of mechanisms design approach things. Okay, we're going to look at certain games. Okay. Okay, so here's the Bayesian model. So here's a kind of outline of the seminar. So we're going to first introduce the general framework for Bayesian game, and we are going to first show that without introducing the exclusion principle, the restriction, we actually you cannot have any identification. Okay, then we propose the exclusion restriction, and we are going to look at whether we can identify the model or not. Okay. And it turns out, as I said, whether you can identify the model crucially depends on when you change the number of bidders, when you change the number of players, whether this kind of action function is going to intersect or not. Okay, and of course, it may have several different situations. The first one is the pattern one is it may have one or more than one intersection point. Okay, the second pattern is there's no intersection point. Okay, and actually, we are going to show you that with the one or more intersection, we can always have a point identification, but with no intersection, you are going to have only partial identification. However, in this talk, I'm going to mainly focus on the point identification with the crossing, okay, because of the time limit. Okay. However, as long as you understand what happens, like for the intersection part, like it's very easy to understand why you cannot have the point identification for no intersection and how you can construct the partial identification. Okay. Okay, so here's the general model. So in the presentation, I'm going to focus on the simple setup, meaning the symmetric setup. Okay. However, our methodology can be extended to allow asymmetric distribution or payoff structure. But let's just fix the idea by looking at the symmetric setup, how this works. Suppose we have I players, okay, and they're anti-symmetric, and they're going to engage in a Bayesian game. And we know that for Bayesian game, one of the most important features is that people have private information, right? So for example, a representative player I has a private type. So this is TI, Okay, so in auction is basically their valuation. Okay, TI belongs to a kind of like a real set. Okay, and we also focus on the IID environment, meaning that the independent private value. Okay, and all the types are drawn from the same CDF function P like F, and also the PDF, and they are kind of atomic and bounded. Okay, and given their private information, everyone is going to choose an action. Okay, and this is denoted as AI, and this is choosing from a compact action space. Okay, and we are going to assume that the player I's payoff function depends on everyone's action as well as his own type. So that's why we have a private valuation game, okay, or private type game, right? Because potentially his payoff can also depend on the other guy's type. But here we are going to exclude that situation. His payoff only depends on everyone's action plus his own type, okay? And yes, Antonio, I think you have a question, yes?
Yeah, sorry, I got a quick question. Maybe you mentioned before, but I forgot. Since you highlighted that you can extend the setup to asymmetric distribution, how about independence? Can you relax independence or not?
So I mean introduce some kind of correlation, right?
Yeah, correlated types, affiliate types.
Yeah, so correlation can be extended like in the same way as a Susan essay and the Hale's paper. Okay, but the most challenging thing is interdependence.
Okay, yeah, I'm not talking about interdependence. I'm just talking about
yeah. Correlation is actually like simple.
Okay.
Thanks, Antonio.
So if I a follow-up question, given Antonio's comment, so interdependence seems to be important in Bayesian games in general, right? So maybe in auctions, in certain settings, independence is not a big assumption, but interdependence seems to be. So what I'm trying to say is, how restrictive are your results, or do you think you could extend your results to interdependence later on? Because that seems to be good. That seems to be important.
Yeah, of course. I mean, actually, in the auction literature, they also try to extend things to interdependence, right? Think about the common value auctions. That's actually like interdependence. But it turns out for interdependence, actually most of the time you actually cannot have identification, and this will be similar in here. But I want to say one thing about your claim that for general Bayesian game interdependence is crucial. But think about you are in a contest, right? Interdependence means that whether my payoff is going to depend on your ability or not, but perhaps not, right? Because my ability only influence my own cost, but the other guy's ability will not influence my cost. So in this case, my payoff is still independent, right? It does not depend on your ability, right? It only depends on your action, but it does not depend on your ability, right? Yeah. So I think for general Bayesian game, the IID still makes sense on a certain situation. Yeah. Thank you, JC. And because we are going to first focus on symmetric, right? We are going to assume that this payoff function is also symmetric in all the other guys' action. Okay, but this can be relaxed later on. Okay, and of course, in a Bayesian game, it's very simple, right? Everyone just choose an action conditional on their private type. So basically, your action will be a function of your type. Okay, so this is action function is denoted as S function. Okay, which is basically a mapping from your type to an action you're going to take. Okay, so basically and here our identification crucially depends on the existence of strictly monotone strategy, which is similar to the auction, right? Because for auction we also need you have the existence of the strictly monotone equilibrium. Okay, here is the same. We are going to introduce this kind of a concept of strict supermajority to guarantee that our equilibrium from the first order condition is indeed strictly increasing. Okay, and later on you are going to see why strictly increasing is very important for this literature. Okay, so in this case we can just simply write the payoff function of player I when his type is Ti and he takes the action AI, right? Of course he needs to take an expectation because he does not know the other guy's payoff. sorry, the other guy's type. Okay, so basically we can write it like in expectation. Okay, but this is a general function. Okay, and of course, when you have the payoff function and everyone is symmetric, then we can just take the first order condition. And this back to Simon's question, right? Yes, we're going to assume that the equilibrium is captured by the first order condition, and we're going to work on the first order condition directly to get our identification. Okay. So basically, we're going to assume that like the first order condition, first order condition is going to capture the equilibrium, and this proposition just tells you, okay, with the appropriate like assumptions from the literature, we know that there always exists an equilibrium in strictly like a monotone strategy, especially when we impose the strictly supermodularity. Okay, so basically now we're going to just work on the first order condition. Okay, to get the identification. And in general, like if you have a general structure of pi, right? So this pi function can be very, very general. In general, you will not be able to identify the pi function. Okay, that's why we need to restrict the functional form of the payoff function to get identification. And this is how we introduce the additive structure. Okay, so basically, in order to explore the possibility of an unobservable structure, okay, we are going to assume that the pi function falls into one of the following three categories. Okay, so yeah, I mean, like you can see the kind of functional form over here. So for example, for the first one, your payoff is basically your type multiplied by a known function plus some kind of unknown function. Okay, and this unknown function y function is something we want to recover. Okay, so not only the distribution of variation is is unknown, but also the y function is also unknown in this game. And we're going to tell you exactly like what are those kind of y functions in the like applications. Okay, and it can also take other like two forms. Okay, it does not matter as long as like the payoff function has this kind of structure. Then we can actually have all the results like to be applied. Okay, so over here, let me just try to say that, you know, like although this indeed put some kind of structure on the Bayesian game we can cover. However, many of the well-known examples actually falls into one of the three categories. Okay, so for example, I have several applications over here. Think about the Atalo contest. Okay, so here, like I do not take the expectation. This is the small pi function. Okay, so in the contest, contest, your payoff is basically your value for winning. Okay, multiplied by your winning probability. Okay, winning probability is basically your own effort over the total effort of everyone, and then minus your cost function. Okay, so in most of the Talo contests, you know, like people assume R is equal to 1, meaning it's the lottery contest. So in this case, remember that this one corresponds to the X function. So in this case, in the Talo function, this term is known, right? So the only unknown structure is the C, the cost function, because how much like how costly for you to exert the effort is something, you know, like the researcher cannot like observe, right? So over here, the C, the cost function will be the Y function, like in the general like framework, and this is something we want to recover, this cost function. Okay, think about like a diamond search. Well, your payoff will be your value of the matching multiplied by your own search effort, then multiplied by for example the average search effort of the population. So basically this structure is known, but as well your cost of search is something you like the researcher cannot know. So we also want to like recover this. Public provision similar, okay, and the differentiated Coulomb competition similar. So in all of these kind of like applications, it falls into one of the categories like we mentioned above. Okay, and it has like the known structure for the X, but the unknown structure for the Y. So the unknown structure for Y is basically this cost function in these applications. Okay, yes, Simon.
So, I mean, that would always be a little my hesitation with these approaches, right? I mean, one is very specific about some details that one has knowledge or no knowledge about, and other details that we don't have knowledge about. So what tells me now here, for example, in the TULAC contest, that we know the contest success function, so we know little r, but we don't know little c.
Yeah.
Or similarly for the diamond search. But why? What prior knowledge do we have to inform us as researchers that we know one but not the other?
Yeah. So basically, like back to your contest, right? So for example, this is kind of R. So usually think about political contests, right? Like usually you can actually observe like how much money each of the candidates like raised, right? You can also observe whether in the end they succeed or failed. So from here you can actually directly estimate what is the R, the successful like function. But cost of function is something, you know, like this kind of intrinsic things, right? Like how costly for you to raise money. This is something you really do not know, like you have no idea like how the cost of function would look at. Well, like some of the paper, for example, the He and Huang's paper directly assumes that this C function is a linear function. Okay. Well, but that's also a very popular contest model, right? You just assume the cost is linear. That's fine. But for empirical work, the cost of function is something, you know, like you usually do not know.
Okay, so that seems a convincing argument for the TULAC contest. How about the other application, or one other application?
Yeah. So for example, diamond search, right? So perhaps like in the data, what you can observe is well, like in some of the papers, you can, for example, directly assume this G function is basically the average effort, right? So if you want to that. If you do not want to that, then basically you need some kind of other information. For example, the matching rate in the market, right? And also like if you can also observe how many hours people spend on search, and you also observe the matching rate, then basically you can recover this G function. But one simple way is just, okay, you just assume this kind of the average effort, right? So yeah, but for the cost function, actually you cannot do the similar justification, right? Because this is really some very personal, right? This cannot be obtained from the aggregated data.
Yeah. Okay. Good. Thanks.
Yeah. Thank you, Simon. Yeah. Very like insightful question. Thank you very much.
So just to follow up on Simon's question. So here, in the three examples, all the X function is continuous. Is that an important assumption?
Continuous. Actually, for this one, it's not necessarily continuous, right? Because we know that a TULAC, right? When everything is zero, it's actually not continuous. Okay, but
that never. But
yeah, but I think it's actually not very important. So let me see. As long as it's continuous, but we do need this kind of function to be continuous in the action. Otherwise,
I'm thinking about auctions. So if my action is higher, my bid is higher than yours, then I win auction. Is that?
I see what you mean. I see what you mean. Yeah. So actually, like so, for example, for this R goes to infinity, we actually know that the TULAC goes to open auction, right?
Yes.
Actually, like I think this will actually make a difference. So remember that in auctions, when you write down the first order condition, right? So remember that the first order condition over here is in terms of an integral equation. But if you have an open auction, actually this will be reduced to a differential equation.
So that's not. So I just want to know whether you include auction as a special case or not. That's my question.
Yeah. So basically, like in this paper, we actually exclude like auctions because we know that auction is something well developed. Okay, because we do want to have this kind of first order condition to be like represented as an integral equation instead of a differential like equation. But however, if you take a limit, okay, everything will be the first order condition will be turned to be a differential equation, will be reduced to a like a differential equation. Okay. So what I want to say is like the auction case will be a limiting case of our paper.
But limiting case is slightly different from special case, right? So
that's right. That's right. Because you still need to use like utilize the convergency like arguments. But in this paper we actually simply like assumes that the pi function is continuous. So that actually excludes auctions.
Yeah, but it can approach the discontinuous ones. Okay.
Yeah, I think so. And auction is something well known. So actually there's no need to integrate the auction as a special case.
Yeah, I'm thinking about the discontinuous Bayesian games.
Yeah, here everything is continuous. But for Talog, it's fine because it's only discontinuous in one point. Okay, so for that case we can still cover. Okay.
Yeah, of course. Thank you.
Jun, so it's slightly inelegant that you consider 3 cases instead of having 1 case that will nest all the cases. Do you have like different proofs for each of the cases, or you actually just don't know how to nest 3 cases into 1 case? And also, so it's a little bit strange that here you impose assumptions on pi rather than on the marginal utility, because we know that only the marginal utility matters for behavior. So maybe it would be, maybe you'll have more elegant cases if you impose assumptions on the marginal utility rather than on the utility.
Yeah. Let me write that down. Yeah, I think instead of impose assumption on the pi, maybe marginal. That's right. Yeah, maybe that could unify this kind of 3 cases, right? Yeah, I think that's very good suggestions. Yeah, but as you said, like yes, the reason like why we have these 3 cases because we actually cannot find out a good way to unify them. Yeah, but maybe following your suggestion, yes, yeah, we should definitely think about it like along that way. So in the paper actually like that also makes the paper less elegant. Is actually we actually like assuming that we in the main paper we just look at structure 1, and then we have a online appendix dealing with the other two structures. Okay, but if we can have a unified one, that would be great. Yes, thank you very much, Anton. Okay, so and also like in the presentation, I'm going to focus on the first one. Okay, and also a more specific like example. So here, well, okay, we need to run a little bit. So here's the non-identification. So just this means you know, like if you do not impose any further restriction, the model is not identified. Okay, and one thing I want to like point out why the strictly increasing strategy is important is like here. So here is the distribution of the action. Okay, we can represent it like in this way. So what I'm saying like is that the action distribution evaluated at the equilibrium is the same as the distribution of the type. Okay, so basically from here to here, and this is valid only when you have a strictly increasing like action strategy. Okay, so that's why the strictly increasing strategy is important for our results. Okay, and if you have this, then we can actually rewrite the first order condition. Instead of using the taking expectation over the type, we can actually take expectation over the action distribution. Okay, because action is a function of the type and also our random variable. Okay, so we can just write the first order condition in terms of the action distribution. Okay, and remember that the action distribution is observable. Okay, so basically so if you do not like put any further restriction, then basically this slide shows tells you that this model is not identifiable. Okay, now let's go to the situation we are going to impose the exclusion restriction. Okay, so just a second. Okay, yes. So here, not only I'm going to focus on the first structure, but I'm going to focus on a specific application. Okay. However, everything over here can be extended to all of the three general frameworks. Okay. So just let's take the Talog context as an example and illustrate to you how we can do the identification. Okay. So basically, like we have a Talog context, and let's Ti denote the private value of the price. Okay. And of course, this is kind of real number. and the action as the effort of this kind of constant contestant, then we can write the payoff function in this way. But remember that over here, everything is taking its interpretation over the action. Okay, action is a random variable. Okay, and over here, what we need to recover is the underlying distribution as well as this C function, right? And we are going to impose that this C function is increasing and convex. So the equilibrium can be written in this way, okay, using the action distribution, okay. And also to simplify the notation, because we need to look at when you change the number of bidders or players, how this is going to change your action, right? So basically, we are going to use this I to denote the number of bidders, okay? For example, when you have a 10 bidder and 5 bidder, the first order condition will be different, okay? So in this case, the identification of the Taylor concept model is to determine the structure F, which is the underlying distribution of the type, as well as the cost function from the observables. The observables over here are how many people you are in this context I, and also you can also observe the equilibrium effort distribution, right? So the action distribution. Okay, so as I said, we need to introduce the exclusion restriction. Okay, that means we're going to have 2 data sets. Okay, one data set contains the number of bidders to be I1. The other one has I2 bidders, players. Okay, and the exclusion restriction means that the participation is exogenous, meaning that the latent private evaluation distribution first satisfies that it's independent of the number of players in the game. Okay, meaning that players are not endogenous choosing their participation. They participate just because of random exogenous reasons. Okay, and in this case, because we have 2 different number of bidders, then we potentially have 2 different distributions, right? Because the distribution also depends on the number of bidders. Okay, so we are going to use S1 to denote the distribution. To denote the strategy when you have I1 bidder. S2 to denote the situation you have I2 bidder. Okay, and also we are going to use the G1, G2 for the distribution as well. Okay, so so turns out instead of working on the distribution, these actually are a common techniques in econometrics. You work on the quantile function. Okay, quantile function basically tells you that this alpha. Okay, this alpha is the quantile of the private value distribution F, such that Ft alpha is equal to alpha. Okay, so basically this is the quantile function of the distribution. And in this case, you can also write down the actions, the action function as a function of the quantile as well, right? And then what you need to do is when you look at the changes of the number of players, you're going to look at how the quantile function changes with the number of bidders. Okay. And we know that the quantile function can also be observed directly from the data. Okay. So in this case, we can rewrite the first order condition using the quantile function. So this can take a rewritten of the first order condition, and then we need to discuss when you change the number of bidders from I1 to I2, how this 2 functions is going to relate to each other. Okay, and over here, because we are dealing with a general Bayesian game, turns out that they can have any possible relationship. But remember that all of these 2 functions are increasing, right? So two increasing function, for example, you can have no crossing at all, right? Or you have a single crossing, right? Or you maybe have a multiple crossing, right? But they are all increasing functions. And turns out for general Bayesian game, all of these 3 pattern can arise, and we need to talk about them one by one. Okay. So for example, if you have the single intersection point, of the bidding function, okay, then this is actually equivalent to their CDF function cross only once. Okay, so basically you have the equivalence. If the action function cross once, then their CDF function also cross once. Okay, and if the action space do not if the action function do not cross with each other, that's actually equivalent to their CDF function of the action do not cross. Okay, and turns out that the identification will crucially depends on whether these two functions cross with each other or not. Okay. So you may ask, okay, how can we determine the pattern of the crossing? First of all, theoretically. Well, what we have shown in the paper is that if you have a differentiated Coulomb competition, okay, there is no intersection. If you have a diamond search and you assume that the G function is basically the total search like intensity of the others, then basically also no intersection. If you have public good provision and you have this particular production function, is also no intersection. But for Taylor context in general, you could have both no intersection and one intersection. Okay, so this is the theoretical results. However, this does not necessarily imply that the no intersection is more relevant in application, because we actually need further assumptions on the structure, right? However, this does suggest that the no intersection case is actually important, if not more important than the intersection case. Okay. So this is from theoretical point of view, how you can determine the crossing or not. And another important observation we made is what I just said. Because theoretically, it's not easy to justify which structure you have, right? But empirically, it's actually very easy, because we can. I just mentioned to you guys the two equilibrium action strategy intersect with each other if and only if their action distribution intersect. And remember that the action distribution is something you can already observe in the data. So basically, like if you are working on the data, it's actually very easy to figure out whether they cross or not, which pattern you are having, by running a simple test. Okay. So now I'm going to tell you, okay, so in this presentation, I'm going to talk only about the intersection part and tell you how we can achieve the identification. Okay. So remember that we have two different numbers of players. That means we have two different first order conditions. Okay, so we can just stack them together. One observation over here is the T over here is independent of the number of players. So that means we can just use the ratio to erase this T alpha over here, right? We can just take the ratio over here, and our first order condition becomes this. So what is this? So this over here, this guy over here is something observable, because it only depends on the action and the action distribution. So from the data, you can actually directly compute what is this term over here. That means the right-hand side is something we do not know, right? Because it's C function, right? C prime function, and it's the ratio. So from here, we can see that this ratio function can actually directly identify from the data, because the left-hand side is already identified, right? So C prime over C prime can be identified directly. However, what we want to identify is what? Is C or C prime, right? So the identification turns out to be whether you can actually identify C prime function from the ratio, okay? Because the ratio can be identified from the observed data, okay? And how can we do this? So we can do it like follows. In order to identify the cost function, the marginal cost function. So here essentially the marginal cost function. We can construct a strictly decreasing construction sequence, okay? And it satisfies the following like relationship, okay? Remember that we have two bidding functions. We have two action functions, right? A1 and A2. We are going to let A1, alpha n is equal to A2, alpha a plus 1. And we know that what we want to identify is this C prime function, right? However, C prime function can be represented in terms of the ratio, right? It can be written as this way, okay? Remember that this guy over here is equal to this guy over here, okay? By construction, okay? This guy over here is equal to this guy over here. This guy over here is equal to this guy over here, and so on and so forth. Okay, so basically we can write down this C prime function, marginal cost function in terms of ratio. Okay, however, the only thing that's left over, sorry, this should not be here. The only thing like left over is this kind of a C prime IP. IP is the intersection. Okay, so basically, we can represent this C prime function as the ratio, but remember that the ratio is already identified, and the only unidentified stuff is this C prime and at the intersection. However, this is basically a scale, right? Because you have a known point, and you just need to have a kind of scale for this point. So basically, we can say that this C prime function can be identified up to a scale from the observable variables. And here's a graphical view of how do we construct the sequence. Remember that this is something we want to have, right? But remember that we can represent this point using the ratio between this point multiplied by this point. But this point is, by construction, is equivalent to this point, right? And then we can represent this point using the ratio again, and then we are going to this point. But in this case, this point is the same as this point, right? But again, we can use the ratio and so on and so forth. So this is exactly how we constructed the ratio. And as you can see, the intersection over here is very important, because when you have the intersection, when you take this kind of a when you take this like a sequence, it's going to converge to this kind of intersection. So that's why with the intersection, we can always have the point identification up to a scale. Okay, and in this case, you can identify C prime with when you have the C prime, then you can directly identify the distribution. Okay, so this is our theorem. Okay, so this just says that yes, like when you have the intersection of the two action functions, then basically you can identify the model up to a scale, which is the scale is something like the marginal cost at the crossing. Okay, and everything else will it can be identified.
For applications, is there some way to determine the scale?
So if there is a kind of crossing, well, if you are doing the data work, it's very simple, right? Because from data you can directly identify where is the crossing.
Yes.
Right.
And that's going to give you the scale.
The scale is something not identifiable, but as long as you have so basically you can put it in this way, the cost function will be the cost function can be fully pinned down. However, it's multiplied by a constant.
What I'm thinking is that suppose you identify that C prime is a constant, and then we know it's in the linear family, but we don't know the slope. So there's some way to pin down the slope from the data. That may be important for the application.
That's right. Yeah. So if it turns out your data is generated from the linear cost function, then actually then our conclusion, then the implication of our data is actually you are not quite sure about the slope.
You're not sure about it.
That's right.
Okay.
Yeah, because that means the same data can be generated by varying the slope and the distribution simultaneously.
Right. The scale has to come from somewhere else.
Yeah, because remember that there are two things you can change, right? One is the distribution. The other one is cost function. But as long as you fix one, the other one can be fixed, right?
Thank you.
Yeah, thank you. Yeah, so this just tells you that yes, with the intersection, yeah, you can always have a point identification up to a scale, okay? And for the no crossing, actually, the first thing we can say that you cannot have a point identification, and this graph tells you exactly why, right? Because with the same logic, right? For any point over here, yes, you can construct the converging sequence, right? But remember that in the end, you're going to end up in a point in this range, okay? Mean that for any points over here, yes, you can represent everything in ratio and a point over here. However, there's no way you can identify this range. Okay, that's why you cannot have a point-wise identification, because for this range, you cannot have identification. Okay, And however, in this case, we can use the methodology in econometrics to build up partial identification results. Okay, but I don't have time to talk to this, and it's more like technical. So I'm just giving you the results.
Just a quick question for the previous picture. Suppose A lower bar 2 equals to A lower bar 1. In the next picture?
Here.
The next one?
Yeah, so
non-intersection one.
Oh, non-intersection one. Yes.
Yes. So suppose the 2A lower bar are the same.
Yeah, then you're back to the intersection part, right?
Right.
So that's actually the option.
Right. Okay. Then in that case, you can also identify.
Yeah. Here we are. So this is the case like they do not intersect, because the intersect at the lower bound is also intersection.
Okay. I get it.
Yeah, and actually that's exactly in GPV paper. They always have the identification, because for first price auction, your bid at the lowest value is always the same, regardless what is your type, like how many bidders are there. So they always have the intersection. Okay, so and this is the crucial difference between the general Bayesian game and the auction, because for general Bayesian game, you cannot guarantee that they are going to intersect at the bottom. Okay. Yeah. So this theorem just says that yes, we can actually create a bound for the identification, and we can achieve the sharp bound, and like we can have achieve the partial identification. Okay. And I think I'm right on time. So just extensions, as I said in the presentation, I focus on very stylized framework. But it turns out that same thing can be extended to allow corner solution. Okay, for example, you have some people can in contest some people do not participate, right? That's zero, and also can accommodate like an asymmetric private type distribution, asymmetric function of yi, asymmetric function of xi as well, and also at the same time we can also extend to unobserved heterogeneity, also endogenize the participation. When you assume the number of the number of bidders do not change the type of distribution. So yeah, so here's the conclusion. I not think I need to spend too much time on this, especially just have some kind of questions instead.
Any questions?
Yeah. Well, just going back to my my earlier point, I think it'd be my earliest point about the Larson Zhang paper that takes a very different approach, doesn't rely on the equilibrium structure. So I think it'd be useful, for your impossibility results, etc., for the negative results at least, to be able to highlight the difference between your approach and theirs, right? There must be something structural in your approach that they circumvent and that allows them to do things that you
yeah,
you
definitely
can't do.
Yeah, definitely I'm sorry, I should not know the paper, but definitely I should take a look at the paper. So can you remind me what's the title of the paper?
Yeah, I can send you the link to the paper.
Okay, yeah, then that will be very much appreciated. Yeah.
And just a quick question. Do you know the convergence rate when you non-parametrically identify it? That's always something we want to know, because the size of data may be limited.
Yeah, so that's about the estimation. Yeah, so that's actually something we are my co-author and I are actually working on. How, given that identification, can we get a better convergence rate than for example GPV, right? So one thing I can tell you is we are also working on another paper, which is we actually assumes non-structure, okay, but we deal with a general Bayesian game. And this Bayesian game, we actually do not need to impose any assumption on, for example, additive structure. Okay, in that case, there are two results. The first one is yes, we can actually utilize this kind of methodology to recover any arbitrary Bayesian game, and the convergence rate will be much faster than what is achieved in the GPV paper. Because in the GPV paper, they need to rely on the estimation of the density function. However, for Bayesian game, you only need to estimate the CDF, and the CDF actually has a much higher like a convergence rate. So basically, our results are actually much more accurate in the application of Bayesian game compared to the auctions.
Great.
Okay, so let me stop the recording here and thank